Just before sunrise, in the freezing darkness of the Tehuacan Desert, something unexpected happened. After hours of observation, exhausted and barely able to feel their hands, astronomers finally captured clear images of interstellar Comet 3I, Atlas. And what they saw didn't match anything we were prepared for. The comet's tail wasn't normal, it wasn't faint, and it definitely wasn't behaving like a typical visitor from our solar system. It was longer, sharper, and disturbingly structured. Even more unsettling, 3I, Atlas, is moving so fast that within a single month, it will be near Jupiter. That kind of speed is rare, but speed isn't what's worrying scientists. It's the way this object behaves. Jets that curve instead of dispersing, activity levels that don't match its size, patterns that seem too organized to dismiss. NASA and the European Space Agency have their explanations. Harvard scientists have others. And, for the first time, amateur astronomers are seeing the same anomalies with their own equipment. Tonight, we're not looking at simulations. We're not relying on official press releases. We're looking directly at the evidence. Because once you see what's strange about 3I, Atlas, the question stops being, what is this comet? And becomes, are we really sure it's just a comet at all? By the time the clock was closing in on 5 in the morning, the cold had already won. It had been a long night in the Dolina de Tehuacan, clear skies, freezing air, and hours spent waiting for a faint object moving silently across the stars. Using a 14-inch Celestron telescope, provided by fellow astronomers, the team had been tracking 3I, Atlas, for nearly an hour. Fatigue was setting in, hands were numb, but no one wanted to stop, because the comet wasn't behaving like they expected. When the images finally came in, exhaustion disappeared instantly. The tail of 3I, Atlas, wasn't short or diffuse. It was extended, unusually long, and shaped in a way that felt wrong for a normal comet. This wasn't a subtle difference only visible to giant space observatories. This was something clearly visible through semi-professional equipment. That alone was shocking. If an interstellar comet can produce features this strong, this structured, and this bright, then whatever's driving its activity is far more intense than what we typically see in objects of this size. And the timing made it even stranger. Based on its trajectory, 3I, Atlas, is moving so fast that in roughly 1 month, it will be near Jupiter. For comparison, our fastest spacecraft take years to reach that region. This object is crossing the solar system like a bullet. Speed alone confirms its interstellar origin, but speed doesn't explain behavior. The comet's activity suggested something deeper, something unusual in its composition, or something unusual in how it releases energy. That's why the team didn't stop at observation. They took the data back to the studio, because once the images were analyzed side by side, they revealed details that echoed warnings already raised by scientists at Harvard. Details that hinted at anomalies far beyond simple ice and dust. And that's where the real mystery began. Once the team returned from the desert and laid the images out on proper screens, the mood changed completely. This wasn't just a beautiful comet, it was a problematic one. The photographs showed something astronomers don't expect from an object like this. Not a soft, chaotic cloud of gas and dust, but structured jets, narrow streams emerging from the nucleus with clear direction and consistency. That detail mattered. In a typical comet from our solar system, the tail is shaped by solar wind. Gas and dust are pushed away from the sun, forming a diffuse, uneven plume. Messy. Unpredictable. But 3I, Atlas, showed something else entirely. Alongside the main tail, there was a second feature, an anticola. An anticola is rare, but not impossible. Normally it's short, faint, and only visible when Earth's viewing angle lines up just right. Here, it was different. The anticola was long, stable, and sharply defined. Not a brief optical trick. Not a faint alignment effect. It persisted. Even more striking, this structure wasn't only visible in data from massive observatories like Hubble. It appeared clearly in images taken with semi-professional telescopes. That means the activity driving it is powerful. Too powerful, some argue, for an object of this size. And then there was the curve. One of the jets appeared slightly bent. Not dramatically, just enough to raise questions. Was it rotation of the nucleus? Hidden magnetic effects? A complex geometry of ejection? Or something else entirely? Each possibility opened a new puzzle. This wasn't speculation pulled from thin air. It mirrored concerns already voiced by scientists like Avi Loeb, who had previously pointed out anomalies in space telescope images. The difference now was simple. These weren't abstract discussions anymore. People were seeing it with their own eyes. And once you accept that the jets are real, stable, and unusually organized, the next question becomes unavoidable. What kind of object can maintain that level of control over its own emissions? Because the answer isn't obvious, and it leads directly into a much deeper mystery. Once scientists began mapping the path of 3I ATLAS, the mystery stopped being just about appearance. It became about probability. Our solar system isn't random. The planets move within a thin, flat disk called the ecliptic. Most objects that enter from the outside come in at wild angles, slicing through that disk like knives. That's what interstellar visitors are supposed to do. But Tri, Atlas didn't. Instead of crashing through at a steep, chaotic angle, it slipped into the system almost gently. Its trajectory deviates by less than 5 degrees from the planetary plane. The odds of that happening by chance are tiny, roughly 0.2%. You could call it luck. But this was only the first improbability. The comet is moving retrograde. While every major planet orbits the Sun in the same direction, 3I Atlas chose the opposite lane. Retrograde objects exist, but combining retrograde motion with such a clean alignment to the ecliptic is extremely rare. 2 low-probability events stacked on top of each other. And then there's the timing. At the most critical moment, perihelion, its closest approach to the Sun, 3I Atlas, became almost impossible to observe from Earth. The Sun's glare blocked our view just as the object reached peak activity. Yet from other positions in the solar system, it remained visible. Mars, Jupiter, clear viewing angles. That coincidence unsettled many observers. Was it just bad luck for Earth-based telescopes? Or was the geometry of this pass unusually convenient for observers elsewhere? From a purely gravitational standpoint, the object's motion doesn't fully add up either. Tiny adjustments in its trajectory have been detected. Not large enough to scream propulsion, but precise enough to demand explanation. NASA attributes them to outgassing. Jets releasing material unevenly can nudge a comet's path. But here's the problem. To produce adjustments of this magnitude, an object this small would need to expel an enormous amount of material. So much that it should be visibly tearing itself apart. And it isn't. The nucleus remains intact. The jets remain narrow. The activity remains controlled. That combination is difficult to reconcile. And once you follow its projected path forward, the geometry gets even stranger. Because 3I, Atlas, isn't just passing through. It's heading toward a very specific neighborhood, Jupiter's. As projections extended forward, attention shifted away from where 3I Atlas came from, and toward where it's going. In March 2026, the object will pass within roughly 53 million kilometers of Jupiter. That number matters, because it places 3I, Atlas, almost exactly at the boundary of Jupiter's hill sphere, the invisible region where the planet's gravity begins to dominate over the Sun's. This isn't just a flyby zone, it's a gravitational threshold. Inside that boundary exist the Lagrange point stable regions where objects can linger with minimal energy. Natural debris rarely arrives there by accident. Yet 3I, ATLS, adjusted its course from solar proximity to line up with this zone. That adjustment wasn't predicted by early models. Something nudged the trajectory. Again, NASA points to non-gravitational forces from outgassing, but the numbers strain that explanation. To steer an object this precisely using sublimation alone, the comet would need to release massive amounts of gas at exactly the right times. That level of control is unusual, especially for an interstellar object with no prior interaction with our Sunday. The alignment raises a quiet but serious question. Is 3I, Atlas, simply passing Jupiter? Or is Jupiter part of its path? The timing is precise. The geometry is clean. The approach avoids chaotic close encounters while still exploiting gravitational structure. If this were a spacecraft, it would look like a gravity-assist setup. No one is claiming that. But the resemblance is uncomfortable. And Jupiter isn't just any planet. It's the largest gravitational hub in the solar system. A natural observation post. A place where an object could linger, redirect, or simply gather information. Even if 3I, Atlas, does nothing at all during this encounter, The fact that it arrives at this exact boundary forces scientists to confront the same issue again. Chance or design? And that question only grows louder when we examine what the comet is doing right now. Because while it travels toward Jupiter, something else is happening. Something that looks less like waste and more like structure. As 3I, Atlas, continued its journey away from the Sun, observers noticed something that pushed the discussion into uncomfortable territory: the anticola. In simple terms, an anticola is a dust feature that appears to point toward the Sun instead of away from it. In normal comets, this happens briefly and faintly, usually as a visual alignment effect. It's weak, short-lived, easy to dismiss. But that's not what's happening here. The anticola of 3I, Atlas, is narrow, highly collimated, and astonishingly long, stretching hundreds of thousands, possibly over 1,000,000 kilometers. This isn't a soft cloud, it's a beam. Natural comet activity produces messy plumes. Jets emerge from random fractures. Dust spreads unevenly, but this structure holds its shape. Its width is tiny compared to its length. Its direction remains stable, and it persists far longer than models predict. From a physics standpoint, this is a problem. Launching material directly toward the Sun makes no sense for a natural object. The solar wind is strongest in that direction. Radiation pressure is brutal. Any loose dust should scatter immediately. Yet the anticola remains intact. Some have suggested it's simply an extreme case of dust alignment. Others argue it's a projection effect. But neither explanation fully accounts for the precision. And that's where the speculation begins, not about intent, but about mechanism. If 3I, Atlas, is traveling into a stream of charged particles at nearly 70 kilometers per second, the interaction energy is enormous. For an icy nucleus, that energy should be destructive. But what if the anticola isn't waste? What if it's protective? A directed outflow could act as a buffer, a way to deflect radiation, disperse charged particles, or stabilize the object against thermal stress. That idea alone doesn't prove anything artificial, but it reframes the structure. No longer debris, no longer randomness, function. And once you consider function, another anomaly becomes impossible to ignore: the orientation. Because the axis of 3I, Atlas doesn't just happen to line up with the Sunday, it does so with disturbing precision. When scientists analyzed the orientation of 3I, Atlas, as it entered the solar system, another anomaly surfaced. Its rotational axis was pointed almost directly at the Sunday. Not approximately, not loosely aligned, within about 8 degrees. For a randomly tumbling interstellar object, that alignment is highly unlikely. The odds are well below 1%. But even that wasn't the most unsettling part. As 3I, Atlas, passed perihelion and the Sun's gravity bent its trajectory, something remarkable happened. A second jet appeared. This new jet activated on the opposite end of the object and once again pointed toward the Sun with nearly the same precision as the first. That matters, because the gravitational deflection of the object was about 16 degrees, exactly double the jet's alignment tolerance. In simple terms, as the object's path shifted, the active emission switched poles to maintain the same solar-facing geometry. That's not how random outgassing works. Natural sublimation should occur wherever sunlight heats exposed ice. Heat should diffuse. Activity should be broad. But here, the emissions behave like switches. Active when exposed, silent in shadow. That kind of on-off behavior requires something unusual. For a jet to shut down instantly when shaded, the source must be thermally isolated from the rest of the body. Perfect insulation. That level of thermal control doesn't naturally evolve in rocks drifting through space. It's something engineers design intentionally when they want heat contained and directed. And there's more. The symmetry is too clean. 2 matching emission points. Mirror behavior. Timed activation. As if the object were designed with redundancy. As if maintaining orientation toward the Sun mattered. At this point, the conversation shifts. Not toward certainty, but toward thresholds. Because one coincidence can be dismissed. 2 raise eyebrows. But repeated geometric precision starts to strain probability itself. And then there's the final layer, the chemistry. Because when scientists examined what this object is actually made of, the results refused to calm the debate. When spectroscopy data came in, many expected it to calm the debate. Instead, it poured fuel on it. In a typical comet, water dominates. Dirty ice, frozen gases, organic traces mixed with dust. That's the standard picture. But 3I, Atlas, didn't follow it. Water was present, but in surprisingly low amounts. Roughly a fraction of a percent. At the same time, the gas plume showed something else. Nickel, not just traces. A strong signal. And the ratio was wrong. In natural space, rocks and meteorites, iron dominates nickel. That's the rule across the solar system. Here, the balance shifts. Nickel appears unusually abundant compared to iron. That alone is strange. But when researchers compared those ratios to known materials, the closest match wasn't primitive cosmic debris. It was industrial alloys, high-temperature, stress-resistant materials, the kind we use in jet engines and turbines. Materials designed to survive extreme heat and particle bombardment. No one is claiming that's what 3I, Atlas is made of. But the resemblance is hard to ignore. Some scientists suggest the nickel could be coming from dust grains bound in a hardened outer layer, a thick crust formed over billions of years of interstellar travel. Others argue that intense solar interaction could be liberating metallic particles in unexpected ways. Yet none of those explanations fully resolve the pattern. There's another detail that deepens the puzzle. The reflected light from 3I, Atlas, shows extreme polarization. That usually indicates a very smooth surface. Not fluffy ice, not loose rubble, something flatter, more uniform. Combine that with the object's unusually high mass and velocity, and the statistics start to look uncomfortable again. Based on current models, an object this dense and this fast should be incredibly rare. So rare that humanity should expect to see one like it once every billion years. Yet this is the third interstellar visitor we've detected and the most extreme of the three. That suggests something important. Either our models of interstellar debris are deeply incomplete, or 3I, Atlas isn't representative of random debris at all. That's when Avi Loeb proposed a hypothesis that made many uncomfortable. What if some interstellar objects are hybrids? Natural on the outside, engineered on the inside. A cosmic Trojan horse. Camouflage perfected by time. If that sounds extreme, remember this isn't a conclusion. It's a stress test. A way to ask whether our tools can truly distinguish between nature and design. Because if 3I, Atlas, turns out to be completely natural, then physics textbooks will need rewriting. And if even one of these anomalies survives scrutiny, then this isn't just a comet. It's a message. Not in words, not in radio waves, but in structure, motion, and mathematics. Right now, 3I, Atlas, is still moving, still heading toward Jupiter, still holding its secrets. And as astronomers around the world race to analyze the data, one truth is already clear. We're no longer just watching the sky. We're interrogating it. So where does that leave us? 3I, Atlas, may turn out to be completely natural. Every anomaly might eventually collapse into a new category of comet physics we haven't discovered yet. And if that's the case, it still changes everything. Because it would mean the universe is far more creative than our models allow. That interstellar space produces objects more complex, more active, and more structured than anything we've seen before. But there's another possibility. That even one of these anomalies isn't random. That even one geometric precision, one chemical imbalance, one perfectly timed adjustment survives explanation. If that happens, then 3I, Atlas, isn't just a comet. It's evidence. Not of visitors arriving, not of signals being sent, but of intelligence leaving traces. Engineering without a signature. Design hidden beneath time and dust. Right now, the object continues its journey toward Jupiter. In March 2026, it reaches that gravitational crossroads. And after that, it fades into the dark, carrying its answers away forever. What remains is the test it leaves behind. A test for science. A test for our assumptions. A test of whether we're willing to ask uncomfortable questions when the data demands it. Are interstellar objects just rocks drifting blindly through space? Or are some of them artifacts, quietly crossing star systems long after their creators are gone? For the first time, humanity isn't laughing at that question. We're calculating it, and whether 3I, Atlas, proves to be nature at its strangest, or something far more deliberate. One thing is already certain. The silence between the stars no longer feels empty. And once you start looking at the universe this way, there's no going back.